So our topic for today is about horizontal alignment, field location of simple curve. So this has something to do with how the engineers are doing the plotting of the stations of the horizontal curve within the curve. So this is how they do it. So let's say we have sorry, let's use a straight line. Okay, so let's mark like um 5 divisions maybe. Okay, let's connect it with maybe color. Let's use a lighter shade. Oh. Okay. So in this scenario, okay. In this scenario, we divided the segment of a circle into, I think, into 5 parts. So let's make an arc. So let's consider this arc. Okay, let's extend this. Okay, so in that situation, we have, let's move it for us to better understand. Okay, so we can like put marks in here. The elements of this is a point of curvature or point of sorry. This is point of curvature. Let's remove this point of curvature. This one is the point of tangency. Okay. Then let's say we have different stations like stations P, Q, V, S. Let's remove this. Say we have stations P, Q, V, and S. So those are the stations that we designated. So let's assume that every station is like 100 feet. Then let's try to make some point of tangency. Or tangent, sorry. Go. Let's try to use this. Similar to this one. Okay, so this one is your vertex. So one more thing to consider is if you are considering deflection angle as deflection angle delta. So this one is also deflection angle delta. So the total deflection angle per station is equal to the sum of the total angle. So let's try to prove something here, like say total angles or deflection angles is equal to delta. Okay, wherein delta is also angle of intersection of tangent 1 and tangent 2. So considering this one as tangent 1 and this one is tangent 2. So apart from that element, I think we missed some element like the offset distance. The E is the external distance, is the external distance. Let's add some more elements. E is the external distance, and if you will add like a color pink maybe, or color blue, connecting this one, so connecting that one, so you can label this where E is the external distance. And M is the middle order. Okay, so considering that station, so we have already figured out stations like station P, station Q, station V, and a station S. So there are some considerations and understanding about the relationship of the angle of deflection with respect to T1 and the chord. So this is the chord and this one is the T1. So the concept is, if this is delta and if you have like a right triangle here, the angle between T1 and the chord is equal to delta all over 2. Okay, so meaning to say the chords the angle between a tangent 1 and the chord of a simple curve is equal to the 1/2 of the total deflection angle. So let's take that note. The angle between tangent 1 and chord is equal to 1/2 of total deflection angle. Okay, so per station. Okay, so following this concept, following that concept, when we will connect these lines. Let's use other colors, for example orange or maybe yellow. When you will connect these lines, let's use thicker and just use yellow. Okay, so that will be the situation. So by definition, on um, field location of a simple curve, so what the engineers will do is maybe the engineer will um, place his measurement on this point of curvature. Then he will measure this length of cord from here to there. Then from PC, from here to another station, from here to another station, from the station, and this to the another station, which is the point of tangency. So meaning to say, when he located the um, when he located the station, all he has to do is like to connect it by a cord or connect it by an arc. So connecting PC to P, connecting P to Q, connecting Q to V, connecting V to S, and connecting S to PT. So with the definition, by the definition of the angle between the tangent one and the chord is equal to 1/2 of the total deflection angle per station. If we are going to analyze this, let's say this one is theta 1 and this one is theta 2, and these three are standard deflection angles for 20 meters or 100 feet. So given the scenario, the alpha 1, the gamma 1 and the gamma 2 are unknown. So you don't know what's the value of the gamma 1 and the gamma 2 deflection angles for the stations starting from PC and ending at PT. Then the deflection letter D is the deflection angle for a 20 meter or 100 feet length of chord or a curve. So it's hard to determine. So given the scenario of the angle between a tangent 1 and a chord is equal to 1/2 the deflection of the angle per station. So meaning to say, if this is entire station, which is the total of gamma, station PC to PT, the angle of deflection is delta. And since the chord connecting PC to PT is and the chord connecting PC to PT, the angle between those two should be 1/2 of the angle starting from station PC to PT. So with that given condition, when you will analyze, say stations, say station PC to station P, station P to station Q, station Q to station V, station V to station S, and station S to station PT, or point of tangency. So when you will analyze, the deflection angles are the following. So deflection angles from station PC to station P, this is the letter P. This one's letter Q, which is this one. Deflection angle is equal to gamma 1. P to Q is D. Q to V is D. V to S is D. And station S to PT is gamma 2. Okay. Let's check for the angles. Between T1 and chords. Okay. Let's move that. Let's say chords. Okay. Chords PC to P. So this one is the chord PC to P. We have chords PC to Q. Chords PC to V. Chords PC to S. And PC to PT. Okay, the angles between T1 and the chords, so PC to P, when we will follow the angle between T1 and the chord is equal to 1/2 of the deflection angle between deflection angle per station. So if this is 1/2, so meaning to say the deflection angle from here to here is equal to gamma 1 all over 2. Okay. Then considering this one naman, I'm sorry. This is gamma plus D all over 2. Considering PC to PV, which is this one, PC, sorry, should be PC to P, PC to C, PC to Q, tama? So PC to V, PC to V. The total deflection angle is gamma 1 plus D plus T. Okay, so this one will be gamma 1 plus D plus d all over 2. Okay. Considering this PC to S, so ito na yun. Sorry. PC to S. Pag PC to S naman, ito na yun. So this one is gamma 1 plus D plus D plus D all over 2. And PC to PT is what? This one. Right? PC to PT is gamma 1 plus D plus D plus D plus gamma 2 all over 2, right? So this one is the angle or the deflection angle between the tangent one and the chord. So PC to PT is gamma 1 plus D plus D plus D plus gamma 2 all over 2. So let's simplify. So this one is simply gamma 1 all over 2. This one is gamma 1 plus D all over 2. Next is gamma 1 plus 2D all over 2. This one is gamma 1 plus 3D all over 2. And this one is gamma 1 plus 3D plus gamma 2 all over 2, which is also equal to delta. Right? So meaning to say, the formula for the delta is is equal to delta all over 2. So meaning to say, delta all over 2 is also equal to gamma all over plus 3D plus gamma So that's the governing formula for solution of the gamma 2. So if you want to if you have like a given gamma 1, and if you have a given D which is constant like 20 and 100 feet, and if you have given if you're given gamma 2, you will be able to solve for the total deflection. So meaning to say, total deflection is equal to 2 times gamma 1 plus 3D plus gamma 2 all over 2. Or simply, total deflection is equal to gamma 1 plus 3D plus gamma 2, which is this one. Okay, so that's a solution for that. So that's simply study of deflection angle uh, using the method done by engineer, because field location of simple horizontal curve are usually located in the field by staking out points on the curve using angles measured from the tangent at the point of curve. So this is it. Starting here, going to the stations, and the lengths of the chords joining consecutive full stations. So these are the stations. The angles are also called deflection angles because they are the angle that is deflected when the direction of the tangent changes direction to that of the chord. Okay, the first deflection angle is this one. The next deflection angle will be considering, let's review again, station PC to P. The first deflection angle is gamma 1. Station PC to Q, the second deflection angle is gamma 1 plus D. Third deflection angle is PC to V, gamma plus 2D, gamma 1 plus 2D. Next deflection angle is PC to S, gamma 1 plus 3D. And last deflection angle is PC to PT, which is gamma 1 plus 3D plus gamma all over 2. So that's another simple analysis of what we call the field locations of deflection angles. Field location of a simple curve. So all you have to do is like to start from PC, then you straight your chords, maintaining your radius, and having different deflection angle, having the different stations lay out on a curve. So that's how they do the field location of simple curve. So apart from that is next topic is the analysis using a simple problem that I can share to you. So it's more of analyzing the field location of using the different samples available in our discussion. So I hope you understand this lesson, and thank you very much. If you have any questions, please comment down below, or you can simply send me a message.